Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Manne Siegbahn, a name perhaps overshadowed in popular scientific law by those of his more publicized contemporaries, stands as a colossus in the history of precision measurement and X-ray spectroscopy. His relentless pursuit of accuracy, coupled with remarkable instrumental ingenuity, reshaped our understanding of atomic structure and paved the way for countless advancements in physics and chemistry. His initial forays into the world of experimental physics centered on the meticulous investigation of the electrical and magnetic characteristics exhibited by metals and semiconductors. This was a field ripe with potential, yet plagued by the inadequacies of existing measurement methodologies. Early in the 20th century, the precise determination of fundamental material properties, such as conductivity and the Hall coefficient, presented formidable challenges. Available instruments often lacked the sensitivity and stability required to obtain reliable data, particularly when dealing with thin films or materials exhibiting subtle effects, temperature fluctuations, parasitic currents, and inherent limitations in the galvanometers and potentiometers of the era contributed to significant uncertainties. Siegbahn recognized that progress in understanding the underlying physics demanded a radical improvement in experimental techniques. His initial efforts were therefore channeled into refining existing methods and devising innovative approaches to minimize systematic errors. Siegbahn's approach was characterized by a relentless focus on meticulous detail and a deep understanding of the underlying physical principles governing his measurements. He embarked on a systematic program to identify and mitigate sources of error, carefully calibrating his instruments and implementing sophisticated shielding techniques to minimize the influence of external disturbances. He devoted considerable attention to sample preparation, recognizing that impurities and imperfections could significantly affect the measured properties. His work involved intricate setups and hours of careful observation. One particularly illustrative example of Siegbahn's early work is his investigation of the Hall effect in thin metallic films. The Hall effect, the generation of a voltage perpendicular to both an electric current and an applied magnetic field, provides valuable information about the charge carrier density and mobility within a material. However, measuring this effect accurately in thin films is notoriously difficult due to the small signal size and the presence of curious thermoelectric voltages. Siegbahn developed a refined experimental setup that incorporated a sensitive potentiometer and a carefully controlled magnetic field. He implemented a clever method of reversing the current and magnetic field directions to eliminate the effects of thermal gradients and contact potentials, achieving a level of precision previously unattainable. Specifically, he used a Wheatstone bridge configuration with a highly sensitive galvanometer as a null detector, meticulously balancing the bridge to minimize any offset voltages. The films themselves were prepared by vacuum deposition onto carefully cleaned substrates, ensuring uniformity and minimizing contamination. This attention to detail allowed him to obtain reliable measurements of the Hall coefficient as a function of film thickness and temperature, providing valuable insights into the electronic transport properties of these materials. The intellectual lineage of Siegbahn's early work can be traced to the pioneering investigations of electrical phenomena by figures such as Heinrich Hertz and Hendrik Lorentz. Hertz's experiments on electromagnetic waves provided the foundational understanding of the relationship between electricity and magnetism that underpinned Siegbahn's investigations. Lorentz's development of the electron theory, which explained the electrical properties of materials in terms of the motion of charged particles, offered a theoretical framework for interpreting Siegbahn's experimental results. Siegbahn built upon these earlier works, refining experimental techniques to test and extend the existing theoretical models. He saw the importance of precise measurement in validating or refining theoretical predictions. Siegbahn's early work on electrical and magnetic properties, while significant in its own right, served as a crucial stepping stone towards his later groundbreaking contributions to X-ray spectroscopy. His mastery of precision measurement techniques, honed through years of meticulous experimentation, provided him with the essential skills and insights needed to tackle the challenges of developing high-resolution X-ray spectrometers. He understood the importance of minimizing systematic errors, carefully calibrating instruments, and controlling experimental conditions, principles that would become hallmarks of his later work. His early work laid the groundwork for his future success. The move towards X-ray spectroscopy was not an abrupt departure, but a natural progression driven by his insatiable curiosity and his unwavering commitment to pushing the boundaries of experimental precision. He recognized the potential of X-ray spectroscopy to probe the inner workings of atoms, providing a powerful new tool for understanding the fundamental laws of nature. The solid foundation he built in solid-state physics provided him with the necessary skills and knowledge to tackle the challenges of developing this new field. The principles of precise measurement developed in solid-state physics continue to resonate in modern scientific and engineering practices. Techniques for minimizing systematic errors, calibrating instruments, and controlling experimental conditions remain essential for obtaining reliable data in a wide range of applications, from materials science to semiconductor device fabrication. For example, modern techniques for measuring the electrical conductivity of nanowires rely on principles similar to those employed by Siegbahn in his early work, but with the added complexity of dealing with nanoscale dimensions. Scanning tunneling microscopy and atomic force microscopy, powerful tools for imaging and manipulating materials at the atomic level, also rely on precise control and calibration to obtain accurate measurements. The legacy of Siegbahn's early work extends far beyond the specific experiments he conducted on electrical and magnetic properties. His commitment to precision, his meticulous attention to detail, and his unwavering belief in the power of experimental investigation serve as an inspiration to scientists and engineers to this day. He demonstrated that progress in science often depends on the development of improved measurement techniques, and that even seemingly small improvements in precision can lead to significant advances in our understanding of the world. His influence on the field of precision measurement is undeniable, and his contributions continue to shape the way we conduct scientific research. The pursuit of ever more refined measurement techniques spurred Manne Siegbahn to shift his focus towards the burgeoning field of X-ray spectroscopy. Existing X-ray spectrometers of the era suffered from a critical limitation: inadequate resolution. This deficiency hampered the accurate determination of X-ray wavelengths, hindering progress in understanding the fundamental properties of matter at the atomic level. To address this challenge, Siegbahn embarked on an ambitious program to design and construct X-ray spectrographs of unprecedented precision. His efforts were directly influenced by the pioneering work of William Henry Bragg and William Lawrence Bragg, whose investigations into X-ray diffraction by crystal lattices provided the theoretical foundation for his instrumental advancements. Bragg's law, relating the angle of incidence of an X-ray beam to the spacing of atomic planes in a crystal and the wavelength of the X-rays, became a cornerstone of Siegbahn's instrument design. A key innovation in Siegbahn's spectrographs was the incorporation of vacuum pumps. The presence of air between the X-ray source, the diffracting crystal, and the detector caused significant absorption of the X-rays, particularly at longer wavelengths. This absorption distorted the measured spectra and reduced the intensity of the signal, thereby limiting the achievable resolution. By evacuating the spectrograph chamber, Siegbahn effectively eliminated this interference, allowing for the detection of weaker X-ray signals and the measurement of X-ray wavelengths with greater accuracy. Further advancements in crystal lattice diffraction techniques were crucial to Siegbahn's success. The quality and perfection of the diffracting crystal directly impacted the resolution and accuracy of the spectrograph. Siegbahn experimented with various crystal materials and cutting orientations to optimize the diffraction process. He meticulously characterized the crystal lattices using optical and X-ray methods, ensuring that the crystal planes were precisely aligned and free from defects. The selection of appropriate crystal materials for specific wavelength ranges was also a critical aspect of his work. One of Siegbahn's early spectrographs, constructed in Uppsala, serves as a prime example of his instrumental ingenuity. This instrument employed a high vacuum chamber to minimize air absorption and a carefully selected calcite crystal to diffract the X-rays. The detector consisted of a photographic plate, which recorded the diffracted X-ray spectrum. With this spectrograph, Siegbahn achieved a significant improvement in spectral resolution compared to existing instruments. He was able to resolve closely spaced X-ray spectral lines that were previously indistinguishable, thereby opening new avenues for investigating the electronic structure of atoms. Siegbahn's instrumental developments had an immediate and profound impact on the field of X-ray spectroscopy. His high-precision spectrographs enabled scientists to determine the wavelengths of X-ray spectral lines with unprecedented accuracy. This capability was essential for testing and refining existing theories of atomic structure and for developing new theoretical models. The precise measurement of X-ray wavelengths also provided a powerful tool for identifying and characterizing elements, leading to the discovery of new elements and the determination of their atomic properties. The influence of Siegbahn's instrumentation extended far beyond his own laboratory. Scientists around the world adopted his spectrographic designs and techniques, leading to a rapid expansion of X-ray spectroscopy as a research tool. His meticulous attention to detail and his unwavering commitment to precision set a new standard for experimental work in the field. He trained a generation of spectroscopists who carried on his legacy, Further advancing the techniques and applications of X-ray spectroscopy, his work on X-ray spectrographs allowed other scientists to accurately determine the wavelength of X-ray spectral lines. This was a significant advancement as it provided a more precise and reliable method for studying the properties of matter. Before Siegbahn's work, the measurement of X-ray wavelengths was a challenging task, with significant variations in the results obtained by different researchers. His spectrographs provided a standardized and reproducible method for measuring these wavelengths, which greatly facilitated the progress of research in the field. The impact of Siegbahn's instrumentation can be seen in the subsequent development of X-ray absorption spectroscopy and X-ray emission spectroscopy techniques that rely on the precise measurement of X-ray wavelengths to probe the electronic structure and chemical composition of materials. These techniques have become indispensable tools in a wide range of scientific disciplines, including physics, chemistry, materials, science, and biology. The development of synchrotron radiation sources, which produce intense and highly collimated X-ray beams, has further enhanced the capabilities of these techniques, allowing for the study of increasingly complex materials and systems. Siegbahn's legacy is firmly established as a pioneer in the development of precision instrumentation for X-ray spectroscopy. His spectrographs revolutionized the field, enabling scientists to probe the structure of matter at the atomic level with unprecedented accuracy. His work laid the foundation for many of the modern techniques used in materials science, chemistry, and physics. His commitment to precision and his dedication to scientific excellence continue to inspire researchers to push the boundaries of measurement and to explore the fundamental laws of nature. Siegbahn's legacy is firmly established as a pioneer in the development of precision instrumentation for X-ray spectroscopy. His spectrographs revolutionized the field, enabling scientists to probe the structure of matter at the atomic level with unprecedented accuracy. His work provided the basis for many of the modern techniques used in materials science, chemistry, and physics. His commitment to precision and his dedication to scientific excellence continue to inspire researchers to push the boundaries of measurement and to explore the fundamental laws of nature. A critical challenge in the early days of X-ray spectroscopy was the inconsistency and unreliability of wavelength measurements. Different researchers, employing various experimental setups and calibration methods, obtained conflicting results, hindering progress in the field. There existed a clear need for a systematic investigation of X-ray spectra and the establishment of precise wavelength standards. Siegbahn addressed this problem head-on, undertaking a meticulous program of measurement and standardization that would transform X-ray spectroscopy into a truly quantitative science. Prior to Siegbahn's work, X-ray wavelengths were often determined using crystal lattices as diffraction gratings. The accuracy of these measurements depended critically on the precise knowledge of the lattice spacing of the crystal. However, the values for these lattice spacings were often uncertain, leading to systematic errors in the calculated wavelengths. Furthermore, different researchers used different crystal materials and different methods for determining lattice spacings, contributing to the overall inconsistency in the field. The existing methods lacked the rigor and standardization necessary for reliable comparison and interpretation of experimental data. Siegbahn's approach was characterized by an unwavering commitment to precision and a systematic methodology. He recognized the importance of establishing a reliable set of wavelength standards that could be used to calibrate X-ray instruments and to ensure the consistency of measurements across different laboratories. To this end, he embarked on a program of meticulous measurement of X-ray wavelengths, employing carefully selected crystal materials and refined experimental techniques. His method involved using high-quality crystals, such as calcite, as diffraction gratings. The angles at which X-rays were diffracted by the crystal were measured with high precision using specially designed spectrometers. The wavelength of the X-rays could then be calculated using Bragg's law, which relates the diffraction angle to the wavelength and the crystal lattice spacing. Siegbahn devoted considerable effort to accurately determining the lattice spacing of his crystals, employing interferometric techniques to measure the dimensions of the crystal lattice with unprecedented accuracy. He then established a standardized system of X-ray wavelengths based on the angstrom unit, a unit of length equal to 1/10,000,000th of a meter. This unit, named after the Swedish physicist Anders Angstrom, had already been widely used in optical spectroscopy. Anders Angstrom's pioneering work in optical spectroscopy, especially his meticulous measurements of spectral lines and his establishment of a wavelength scale, served as a direct influence on Siegbahn's standardization efforts in X-ray spectroscopy. Siegbahn recognized the value of Angstrom's approach and sought to apply similar principles of precision and standardization to the X-ray region of the electromagnetic spectrum. Siegbahn's wavelength tables provided a comprehensive and reliable set of reference values for calibrating X-ray instruments. For example, his table included the wavelengths of prominent X-ray emission lines from a variety of elements, such as copper, molybdenum, and tungsten, measured with high accuracy. These tables allowed researchers to accurately determine the wavelengths of unknown X-ray lines by comparing them to the known standards. The process involved carefully aligning the X-ray spectrometer using the known wavelengths from Siegbahn's tables, then measuring the angle of diffraction for the unknown X-ray line using Bragg's law and the calibrated instrument. The wavelength of the unknown line could be determined with high precision. The impact of Siegbahn's precise wavelength standards on the development of atomic theory and quantum mechanics was profound. His data provided crucial experimental evidence that helped to refine existing theoretical models and to guide the development of new ones. One area where his work had a significant impact was in the refinement of Bohr's model of the atom. Bohr's model, proposed in 1913, provided a revolutionary explanation for the discrete nature of atomic spectra. The model postulated that electrons could only occupy certain allowed orbits around the nucleus, each with a specific energy level. Transitions between these energy levels resulted in the emission or absorption of photons with specific wavelengths corresponding to the observed spectral lines. While Bohr's model successfully explained the gross features of the hydrogen spectrum, it failed to account for the fine structure of spectral lines observed in more complex atoms. Siegbahn's precise measurements of X-ray spectra provided crucial data for testing and refining Bohr's model. His data revealed subtle deviations from the predictions of the original Bohr model, particularly in the spectra of heavier elements. These deviations suggested that the model needed to be modified to account for relativistic effects and electron-electron interactions. Arnold Sommerfeld, a German physicist, extended Bohr's model by incorporating relativistic corrections and introducing elliptical orbits for electrons. Sommerfeld's relativistic corrections, guided by Siegbahn's precise X-ray data, provided a much better agreement with the observed fine structure of spectral lines. The combination of Bohr's quantization rules and Sommerfeld's relativistic corrections represented a significant step forward in the development of atomic theory. Another area where Siegbahn's work had a significant impact was in the determination of fundamental physical constants. His precise measurements of X-ray wavelengths allowed physicists to calculate the Rydberg constant, a fundamental constant that appears in the formula for the wavelengths of spectral lines, with greater accuracy. The Rydberg constant is directly related to the fundamental constants of nature, such as the electron charge, the electron mass, and Planck's constant. By improving the accuracy of the Rydberg constant, Siegbahn's work contributed to a more precise determination of these fundamental constants. This, in turn, had implications for a wide range of physics experiments and theoretical calculations. His work also directly influenced others by providing a solid foundation for future research in X-ray spectroscopy. Physicists such as Arthur Compton, known for his discovery of the Compton effect, directly utilized Siegbahn's wavelength standards in their experiments on X-ray scattering. Compton's experiments, which demonstrated the particle-like nature of X-rays, relied on accurate knowledge of X-ray wavelengths. Siegbahn's data enabled Compton to perform his experiments with greater precision and to interpret his results with greater confidence. In summary, Manne Siegbahn's systematic investigation of X-ray spectra and the establishment of precise wavelength standards were pivotal in transforming X-ray spectroscopy into a quantitative science. His meticulous measurements and standardized system provided a reliable foundation for future research, enabling scientists to probe the structure of matter at the atomic level with unprecedented accuracy. His work had a profound impact on the development of atomic theory and quantum mechanics, providing crucial experimental evidence that helped to refine existing theoretical models and to guide the development of new ones. His legacy as a pioneer in precision measurement and standardization continues to inspire researchers today. Siegbahn's dedication to precision and standardization culminated in the Nobel Prize in Physics in 1924, awarded in recognition of his discoveries and research in X-ray spectroscopy. This prestigious honor served as an affirmation of the transformative impact of his work on the field, elevating X-ray spectroscopy from a descriptive technique to a rigorous, quantitative method for probing the atomic structure of matter. Following the Nobel recognition, Siegbahnn continued his relentless pursuit of refining X-ray spectroscopic techniques. He recognized the limitations of existing instrumentation and resolved to push the boundaries of spectral resolution and measurement accuracy. This endeavor led to the development of innovative X-ray tubes and detectors, each designed to overcome specific challenges in the pursuit of higher precision. One notable innovation was his work on vacuum spark sources, which produced intense, highly ionized spectra, allowing for the study of inner-shell transitions in heavier elements. These sources offered a significant improvement over traditional X-ray tubes, providing a greater flux of photons with narrower line widths. A central problem in X-ray spectroscopy was and remains the inherent broadening of spectral lines due to various factors, including the finite lifetime of excited atomic states and instrumental effects. Siegbahnn tackled this challenge through a combination of improved instrumentation and sophisticated data analysis techniques. He explored the use of curved crystal spectrometers, which employed precisely shaped crystals to focus X-rays onto a detector, thereby increasing the resolving power of the instrument. He also developed methods for correcting instrumental broadening effects, allowing for more accurate determination of intrinsic line shapes and energies. Specific examples of instruments developed in this period include several high-resolution vacuum X-ray spectrographs, each tailored for specific energy ranges and experimental conditions. One such instrument, described in detail in his publications, utilized a large, precisely cut calcite crystal as a dispersive element, achieving a resolving power sufficient to resolve closely spaced spectral lines. Another instrument incorporated a rotating anode X-ray tube, which allowed for higher power operation and reduced thermal loading on the anode, leading to increased X-ray intensity and stability. Beyond instrumentation, Siegbahn also made significant contributions to the development of measurement techniques. He pioneered the use of photographic emulsions as detectors, carefully calibrating their response to X-rays and developing methods for extracting quantitative information from the resulting images. He also explored the use of ionization chambers and proportional counters, which provided direct electronic readout of X-ray intensity, enabling more rapid and precise measurements. Siegbahn's influence extended far beyond his personal research. He played a pivotal role in establishing the Nobel Institute for Physics in Stockholm, later renamed the Manne Siegbahn Institute, which became a leading center for atomic and molecular physics research. Through his leadership and mentorship, he fostered a vibrant research environment that attracted talented scientists from around the world. His institute became a training ground for future generations of physicists, many of whom went on to make significant contributions to their respective fields. His impact on the development of physics research in Sweden was transformative. Prior to his arrival, physics research in Sweden was relatively modest in scale and scope. Siegbahn's vision, energy, and scientific acumen propelled Swedish physics to the forefront of international research. He secured funding for state-of-the-art equipment, recruited talented researchers, and established a culture of excellence that continues to this day. The enduring impact of Siegbahn's work can be seen in areas such as material science and surface physics. His precise measurements of X-ray spectra provided a foundation for understanding the electronic structure of materials, enabling the development of new materials with tailored properties. His techniques for surface analysis, such as X-ray photoelectron spectroscopy, became essential tools for characterizing the chemical composition and electronic states of surfaces, with applications ranging from catalysis to microelectronics. Siegbahn's legacy extends to modern-day research facilities such as synchrotrons. The techniques he pioneered are still utilized and refined at these facilities, enabling scientists to probe the structure of matter with even greater precision and detail. Synchrotron radiation, with its high intensity and broad spectral range, has revolutionized X-ray spectroscopy, allowing for the study of increasingly complex systems and phenomena. The fundamental principles established by Siegbahn, such as the importance of precise wavelength calibration and the use of high-resolution spectrometers, remain central to synchrotron-based X-ray spectroscopy experiments. Furthermore, Siegbahn's influence can be seen in modern-day electron spectroscopy techniques. His early X-ray spectroscopy work was a precursor to the development of techniques such as Auger electron spectroscopy and X-ray photoelectron spectroscopy, also known as electron spectroscopy for chemical analysis. These techniques, which involve the analysis of electrons emitted from a material upon X-ray or electron irradiation, provide valuable information about the elemental composition and chemical states of surfaces and interfaces. The underlying principles and experimental methodologies developed by Siegbahn have been instrumental in the advancement of these techniques. In conclusion, Manne Siegbahn's contributions to X-ray spectroscopy were nothing short of transformative. He elevated the field from a qualitative tool to a precise quantitative method, providing a foundation for countless subsequent discoveries in physics, chemistry, and materials science. His meticulous measurements, innovative instrumentation, and dedication to standardization set a new standard for scientific rigor. His influence on the development of physics research in Sweden and his mentorship of future generations of scientists cemented his legacy as one of the leading physicists of the 20th century. His scientific philosophy, characterized by a relentless pursuit of precision and a deep commitment to experimental rigor, serves as an inspiration to researchers today. He believed that accurate measurements were the key to unlocking the secrets of nature, and he dedicated his career to developing the tools and techniques necessary to achieve this goal. His work exemplifies the power of careful observation, meticulous analysis, and a willingness to challenge existing paradigms. His legacy continues to shape the field of X-ray spectroscopy and beyond, reminding us of the enduring value of precision, accuracy, and a relentless pursuit of knowledge. The impact of his work extends into modern research methodologies, underscoring the enduring relevance of X-ray spectroscopy techniques at facilities such as synchrotrons, and his influence is palpably present in contemporary electron spectroscopy, demonstrably tracing back to his pioneering X-ray spectroscopy endeavors.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.